Something changed after perihelion. For the past 72 hours, multiple observatories, from Mauna Kea to Lucia, have confirmed that 3i Atlas is no longer following the trajectory calculated before its solar pass. The deviation is small on paper, less than half a degree across the sky, yet at interstellar speeds that difference translates to millions of kilometers. The early consensus was a simple one: sensor error, or a brief outgassing event still uncorrected in the models. But the more data that arrived, the less that explanation fit. Infrared readings from the James Webb Telescope no longer align with where 3i Atlas should be. Ground-based optical data from the European Southern Observatory show the same: a slow, steady drift to the southwest relative to its predicted vector. Even the independent amateur network tracking its signal has reported light curve fluctuations inconsistent with natural tumble. As of this hour, no agency has issued an official correction to its orbit, and yet the object we've been following for months is clearly off course. Something, either internal or external, has altered its motion after it swung behind the Sun, and that's where tonight's story begins. Because what's happening now with 3i Atlas is forcing scientists to question whether we're still observing the same object we modelled weeks ago, or something that has changed since we last saw it. The first warning came quietly. On October 31st, the Minor Planet Center received astrometric submissions from observatories in Hawaii, Chile and South Africa, showing positional offsets that didn't match the post-perihelion orbit released earlier in the week. The residuals, those tiny gaps between expected and measured coordinates, were small but consistent. Every night the offset grew slightly larger, as if 3i Atlas had slipped from its plotted curve and was tracing a new path through space. By November 1st, the difference had become undeniable. The updated orbit solution placed the object roughly 0.47 degrees away from its projected location, translating to over 1.3 million kilometers of lateral deviation at its current distance. In celestial mechanics, that's not noise, that's a new trajectory. Analysts at NASA's Jet Propulsion Laboratory compared the fresh data to the original hyperbolic solution derived in July and noticed an increasing divergence in both right ascension and declination. Something that shouldn't happen if only gravitational forces were acting. The immediate suspects were familiar: observational error, atmospheric distortion, or instrumental calibration drift. But cross-checks removed each in turn. The same deviation appeared across different instruments, wavelengths and hemispheres. The Chilean VLT and the Pan-STAR system in Hawaii agreed to within fractions of an arcsecond. It was real. To understand how unexpected this is, recall how stable 3i Atlas appeared before perihelion. For months, its orbit was a model of precision. Even as it approached the Sun at a velocity exceeding 110 km per second, its path obeyed every expectation of Newtonian dynamics. The first signs of change came only after it emerged from behind the Sun in late October, when its light signature shifted slightly blueward and its apparent motion began to stray. The Solar and Heliospheric Observatory SOHO data added a critical piece. During conjunction, when the object passed near the Sun's glare, coronagraph images hinted at a brief brightening event. Perhaps an outburst, perhaps something else. When analysts later overlaid that event with the new trajectory, a pattern appeared. The timing of the outburst matched the moment the deviation began. If it was outgassing, the force must have been precisely directed. Small jets of vapor can nudge a comet slightly, but to alter a hyperbolic interstellar object by measurable degrees requires extraordinary momentum. Modelling teams ran simulations assuming asymmetric CO2 emission. Even with generous estimates, the numbers didn't fit. The impulse needed would exceed anything natural by an order of magnitude. Then came the radar data, or rather, the lack of it. Goldstone's planetary radar attempted to ping the object during its reappearance, expecting at least a faint echo. None came back. Either the surface had become unusually absorbent, or its orientation had shifted so that the cross-section toward Earth was drastically reduced. In both cases, that would align with a change in attitude or internal rotation, not just linear drift. Meanwhile, the Hubble Space Telescope registered a subtle variation in brightness, unrelated to phase angle or distance. The amplitude of its light curve flattened, suggesting that either 3i Atlas had stabilized its spin or its reflective geometry had changed. Both would influence its path indirectly through altered outgassing patterns, yet again not to this extent. To ensure no computational bias, independent groups recalculated the orbit using their own software. The Harvard-Smithsonian team, the European Gaia Consortium, and a handful of private astrophysicists all converged on the same conclusion. The acceleration component wasn't random noise. There was a systematic vector component pushing the object outward from the predicted solar-centric path. The direction, roughly 240 degrees ecliptic longitude, 6 degrees south, matched neither solar radiation pressure nor any plausible gravitational perturbation. If sunlight was responsible, the required surface-to-mass ratio would be extreme, implying a wafer-thin structure rather than a solid nucleus. Yet telescopic spectra still showed the spectral slope typical of dense carbon-rich rock mixed with volatile ices. The material composition hadn't changed. What had changed was its motion. By midnight UTC, major space agencies began updating their internal bulletins. ESA's Planetary Defense Office issued a note labelled Trajectory Uncertainty Expansion Event, a phrase typically reserved for near-Earth asteroids under non-gravitational acceleration. This wasn't a threat warning, it was a data anomaly notice. In plain terms, the path of 3I Atlas could no longer be predicted with high confidence. Within scientific channels, the conversation shifted from curiosity to concern. The object's speed, still above escape velocity, meant any small angular change now would magnify exponentially over time. If uncorrected, positional predictions would become meaningless within weeks. Tracking teams coordinated emergency observation windows before it drifted too far into solar interference. A veteran orbital dynamicist from ESA summarized the situation in an internal briefing. We have an interstellar body demonstrating sustained post-perihelion acceleration, inconsistent with thermal recoil, asymmetric outgassing, or solar radiation pressure. The effect is continuous, not impulsive. His final line was blunt. At present, our models cannot reproduce it. Even within cautious circles, that admission carried weight. When the first interstellar visitor, Oumuamua, exhibited similar non-gravitational acceleration in 2017, it triggered years of debate. But this time, the deviation occurred after solar passage, not before. If 3I Atlas were a conventional cometary nucleus, it should have lost volatile mass and stabilized. Instead, it appears to have gained acceleration as it moved away from the Sun. The next task was verification. Could nearby spacecraft provide context? Solar Orbiter's instruments briefly detected an uptick in charged particle density at the time of the deviation, but correlation isn't causation. The Parker Solar Probe's magnetometer noted a microfluctuation in local field strength, though analysts attribute it to routine solar wind turbulence. Still, both events happened within hours of the observed path shift. At this stage, explanations split into two camps. The conservative model treats the anomaly as extreme outgassing, amplified by shape irregularities, a rotating body venting gas in unpredictable spurts. The alternative model proposes an active internal mechanism, something adjusting its own motion deliberately, or through an unknown physical process. Neither has yet been verified, but data trending continues to favour a sustained acceleration pattern, rather than random thrust. As of tonight, the official ephemerides have been reissued with wide uncertainty margins. Observers are instructed to log positional coordinates manually, rather than rely on automatic telescope tracking. For an object crossing interplanetary space at more than 100 km per second, that's like trying to keep a laser pointer fixed on a grain of sand moving across a football field. Every update adds one more layer of confusion. The object's visual magnitude now fluctuates erratically, sometimes dimming by 2 full magnitudes before recovering. Its tail, if it can still be called that, extends in a direction inconsistent with solar wind flow. And while its brightness curve suggests rotation, the rotation period seems to lengthen gradually, as though some torque is acting against it. The evidence taken together paints a picture of a body that is not only drifting, but evolving in motion. The clean arc plotted months ago has become a frayed line of uncertainty stretching across the solar map. No one can yet say why. Within hours of the first reports, observatories worldwide began to verify whether the deviation seen in 3I Atlas's path was real or a product of human error. Every step of the tracking chain was scrutinized. Telescope logs, CCD timestamps, astrometric calibrations, all rechecked line by line. The first question was simple. Could this be an artifact of data processing rather than motion in space? NASA's Jet Propulsion Laboratory initiated what they call Trajectory Integrity Audit, comparing raw optical measurements from July through late October. Each data point was recalibrated using updated star catalogues from Gaia DR4. Even after corrections, the positional offset remained. The Chilean La Silla Observatory confirmed that their system clocks, synchronized with atomic time, showed no drift that could explain the discrepancy. The European Space Agency's archive produced similar findings. Independent instruments, different longitudes, same result. At this stage, analysts noticed something subtle but important. The measurements from just before perihelion, while 3i Atlas was partially obscured by solar glare, displayed minor inconsistencies in brightness and shape. They weren't significant at the time, but now, when plotted against the post-perihelion path, those small irregularities lined up precisely with the direction of the current drift. In other words, the deviation may have begun before the object passed behind the Sun but remained undetected due to observation limits. The process of rechecking data became almost forensic. Every observatory maintains a record of skyflats and bias frames used to remove camera noise. These were reprocessed to confirm the positions. The final residuals were still there, clear and consistent. No amount of recalibration erased them. 3i Atlas had moved. Meanwhile, a collaboration between the University of Arizona and the Max Planck Institute for Astronomy performed an independent photometric study. Using deep learning algorithms trained on known comet behavior, they compared the pre- and post-perihelion brightness curve of 3i Atlas. What they found was subtle but significant. A slight phase lag in the light curve, as if the object's reflective surface had rotated or its geometry had shifted. The lag corresponded almost exactly to the time when its trajectory began to diverge. That correlation reopened an old debate. During the 2017 Oumuamua investigation, similar photometric irregularities led to suggestions of a thin, possibly artificial structure adjusting its motion under solar radiation pressure. Most researchers dismissed that as speculative, yet the pattern here looked familiar, too familiar to ignore. If solar radiation alone couldn't explain the change, what else could? ESA's trajectory analysts ran a fresh orbital fit using a non-gravitational parameter model, typically used for comets. When they factored in a symmetric outgassing, the fit improved slightly, but not enough to account for the total offset. The thrust required to match the observed motion would have to be directed almost perfectly along the Sun object vector and sustained for days. Natural outgassing doesn't behave that way. It's chaotic, impulsive, and short-lived. During a private teleconference, one researcher described the findings in cautious terms. "We are looking at a coherent directional impulse that persisted beyond expected thermal duration. Either we're underestimating a physical process, or the body's shape and rotation are producing an unknown effect." That phrase, unknown effect, became the unofficial label within internal bulletins. Across the Pacific, Japan's Subaru telescope team took the opportunity to reanalyze their July and August images. By applying motion deblurring techniques and advanced centroid detection, they found the same offset trajectory that now appears in November data. The implication: the deviation wasn't a sudden event. It was gradual, building over weeks, unnoticed because of sparse temporal coverage. At this point, public databases began updating orbital solutions every 12 hours instead of once daily. Even with the updates, predictions were slipping. When amateur astronomers tried to locate 3i Atlas based on the latest coordinates, some reported the object slightly outside their telescope field of view. That kind of small but systematic error is rare in professional ephemeriders. Internally, NASA and ESA both issued confidence reduction notices to indicate that the standard models could no longer guarantee positional accuracy beyond several days. The margin of error expanded exponentially, suggesting that even if new measurements were added, the core model might still be missing something fundamental. Some analysts proposed an alternate explanation: an unmodeled jet of sublimating material directed inward rather than outward, essentially producing thrust toward the Sun. That hypothesis, though creative, ran into a thermodynamic problem. The observed sunlight intensity at that distance would have already reduced most surface volatiles. Unless 3i Atlas contained deeply buried material exposed by internal fracturing, sustained emission was unlikely. Others considered electromagnetic effects. Could the object's metallic compounds, once ionized, interact differently with the solar magnetic field? Laboratory models show that in extreme cases, charged dust can experience measurable acceleration, but the amount required here would demand an enormous, stable field region, something not present in interplanetary space at the observed coordinates. As each theory failed to explain the anomaly fully, the tone of the discussion shifted. What began as cautious verification turned into quiet confusion. The orbit wasn't wrong because of missing data, it was wrong because something changed physically in the object itself. Toward the end of October 31st, the International Astronomical Union's Minor Planet Center received one final batch of submissions from the Las Cumbres Observatory network, which uses synchronized robotic telescopes. The residuals matched all previous reports within a few arcseconds. Statistically, the deviation was real beyond any reasonable doubt. For most comets or asteroids, that would be a minor curiosity. But for an interstellar object, an unbound traveller from outside our solar system, it was unprecedented. If something could alter its path after leaving perihelion, we were witnessing an effect not yet documented in celestial mechanics. The recheck was supposed to resolve uncertainty. Instead, it confirmed it. Every cross-verification pointed in the same direction. 3i Atlas had not only shifted, it was continuing to drift, slowly but persistently. And when analysts plotted that drift across successive frames, they found a new vector emerging from the data. A faint, consistent acceleration away from the Sun, as if a steady force were acting invisibly upon it. The realization led to the next logical question. If the data are correct, and the object's speed is increasing instead of stabilizing, then some external or internal mechanism must be pushing it. When the first acceleration reports appeared, many assumed the explanation would be simple: sunlight. Solar radiation pressure is one of the few forces in deep space that can subtly push an object over time. It acts constantly, and depending on how reflective or porous the surface is, that pressure can alter speed and direction. So scientists turned their attention toward the Sun itself, hoping that the growing deviation of 3i Atlas might be nothing more than the result of intensified solar activity following perihelion. The timing, on the surface, seemed plausible. The Sun had recently entered a heightened phase of activity. Between late October and early November, several medium-class solar flares erupted across its surface, accompanied by bursts of high-energy particles that streamed through interplanetary space. If 3i Atlas had passed through one of those regions, it could have experienced a short-lived push. The challenge was explaining how such a push could continue long after the event itself ended. Solar radiation pressure isn't uniform. It depends on how sunlight interacts with a body's surface. A dense, dark rock absorbs energy differently than a bright, icy one. Observations from the Very Large Telescope and the Pan-STARRS Array show that 3i Atlas has a moderately dark surface, more carbon-rich than reflective. That means the photons it receives from the Sun should mostly heat it, not push it. Even if radiation pressure played a role, it wouldn't be strong enough to cause a persistent acceleration of this magnitude. Scientists then looked at the object's coma, the faint halo of gas and dust that surrounds it. During perihelion, a thin jet of vapour was detected extending roughly toward the Sun, rather than away from it. That was an odd direction. Normally, heat-driven outgassing pushes material outward, forming a tail that points away from the solar light. Here, the jet seemed inverted, flowing sunward as if some internal venting mechanism had activated on the shadowed side. If the gas was vented inward, it could produce thrust in the opposite direction, helping drive the object faster as it receded. To confirm this, infrared instruments from the ESO-FIA Observatory examined the coma's temperature gradient. They found that one hemisphere of 3i Atlas was consistently warmer than the other by several degrees, even days after solar exposure should have evened out. This persistent asymmetry supported the idea that sunlight was being absorbed and re-emitted unevenly, potentially generating a small but steady thermal recoil. However, the pattern still didn't align perfectly with the observed trajectory change. The force required to explain the drift would have to act almost continuously, not in brief bursts. Solar wind was another suspect. The stream of charged particles flowing outward from the Sun carries its own momentum. When those particles strike dust or plasma around an object, they can impart subtle acceleration, yet the density of that wind drops dramatically with distance. By the time 3I Atlas reached its current position, the pressure from solar wind was far too low to produce the sustained deviation that astronomers were seeing. That left the possibility of electromagnetic interaction. The surface of 3I Atlas appears rich in nickel and other conductive materials. When such elements are ionized by solar radiation, they can create localized magnetic fields. If those fields interacted with the Sun's larger magnetic structure, they could produce temporary repulsion or attraction effects. But again, the direction of the force didn't match. Instead of moving along the Sun's magnetic field lines, 3I Atlas was drifting slightly across them. Still, one piece of the solar puzzle stood out. The moment the object passed behind the Sun during conjunction, instruments briefly lost track of it. When it re-emerged, the trajectory deviation had already begun. That timing correlation suggested that something during the perihelion passage, a change in temperature, ionization or structure, altered how the object interacts with sunlight. It may not have been pushed by solar radiation itself, but by what the sunlight triggered inside it. To explore that idea, astrophysicists simulated what would happen if pockets of frozen gas beneath the surface suddenly sublimated due to the extreme heat near the Sun. The release could act like a series of tiny thrusters, each providing a microburst of momentum. But again, the problem was duration. Outgassing events fade quickly once an object moves away from the Sun. Yet 3I Atlas continued accelerating days after the peak heating ended. The solar hypothesis started to lose support. The energy from the Sun could explain the timing, but not the persistence. What puzzled analysts most was the stability of the acceleration. It wasn't chaotic or irregular like gas jets. It was smooth, almost mechanical, as if the force were being modulated or dampened over time. Some scientists began to use the phrase solar push anomaly in internal memos, a term acknowledging the correlation with sunlight, but admitting that standard models failed to explain the sustained motion. To the public, agencies kept their tone neutral, describing it only as a radiative response under review. What remained was an uncomfortable conclusion. 3I Atlas might not just be reacting to solar energy, it might be using it. If its structure had changed during perihelion, perhaps the surface layers now behave like a light sail or thermal engine, converting sunlight into thrust. It would be a natural process if accidental, but the precision and continuity suggested something far more deliberate. For now, all that's known is that after passing the Sun, the object began to act differently under solar exposure than before. The same energy that should have slowed it may have triggered a mechanism that keeps it moving faster, and that shift set off the next round of analysis, an investigation into the source of those uneven emissions seen around the object. Because the more researchers looked, the clearer it became that something inside 3I Atlas was venting in a way that no one had seen before. When the solar explanation began to lose strength, attention turned inward, to the object itself, and the strange, inconsistent emissions coming off its surface. Telescopes across both hemispheres reported a faint shifting halo around 3I Atlas, but it didn't behave like the tail of a normal comet. Some nights, the jet appeared narrow and sunward. On others, it stretched sideways or even flickered out completely. It was as if the object were exhaling through multiple vents that opened and closed unpredictably. The Atacama Large Millimeter Array detected traces of carbon dioxide and carbon monoxide, both expected from a volatile-rich body, but the intensity of those signals fluctuated wildly. A typical comet releases gas rhythmically as it rotates, producing periodic peaks every few hours. 3I Atlas showed no such rhythm. Instead, the jets pulsed in short bursts, often originating from the hemisphere facing away from the Sun. That alone was strange. Outgassing driven by heat should emerge from illuminated regions, not the dark side. When researchers synchronized those emission bursts with the object's estimated rotation period, they found a curious alignment. The events seemed to follow a repeating pattern, though not perfectly. A few minutes before each major burst, a smaller flare of dust preceded it, like a pressure build-up followed by release. The consistency suggested that these weren't random fissures venting gas. They might be structural cavities releasing material in a controlled rhythm. Infrared data supported this idea. After each burst, the surface temperature in localized spots rose sharply and then declined slower than physics would predict. That lingering warmth implied heat transfer from deeper layers, possibly through tunnels or hollow pockets carrying gas upward before expulsion. If true, 3i Atlas wasn't venting like an ordinary icy rock. It was channeling gas internally, focusing thrust through specific outlets that rotated into position with each spin. Computer models using this assumption produced results that matched the observed drift surprisingly well. A sequence of small timed jets could generate a continuous net force, pushing the object along its now shifted path. The problem was efficiency. The total amount of gas required to sustain such propulsion should have created a much denser coma than what telescopes were actually seeing. Either the gas flow was far more concentrated than expected, or something about the object's shape was amplifying the thrust. At this stage, radar data added another clue. Before perihelion, radar reflections from 3i Atlas were moderately strong, typical of a dense, irregular nucleus. After its solar passage, however, those echoes weakened dramatically. That drop in reflectivity hinted that the surface had changed, either coated by a fine dust layer, fractured into a porous crust, or altered by ejecta that resettled onto it. A looser surface could trap gas until pressure built high enough to burst free, producing sharp, pulsed emissions instead of a steady flow. Still, not everything fit. The timing of the jets seemed too regular to be random. They repeated near the same rotational phase each cycle, almost as if the internal build-up and release were being moderated, like a mechanism adjusting itself. Scientists avoided using such language publicly, but internally the phrase venting sequence began circulating. It described what was being seen without implying intent, yet the implication hung over every discussion. This object was behaving like something managing its own momentum. To reconcile the data, researchers proposed a more complex scenario. During its perihelion passage, the intense solar heat could have restructured the interior, creating cavities lined with different materials. Some might retain heat longer, causing delayed sublimation that cycles predictably as the object spins. The result would be periodic thrust aligned with its rotation, explaining both the persistence and the stability of the acceleration. Even so, the physics remained puzzling. The emissions were weak but efficient, directional yet faint. The cumulative force they produced was too stable to arise from chaos alone. In the words of one analyst, it's as though 3i Atlas has found equilibrium in imbalance, venting just enough to keep moving faster, but never enough to destabilize. By early November, the phenomenon was undeniable. The jets weren't random flares of heat. They were part of a pattern, one that repeated, faded, and returned with uncanny precision. And that pattern led scientists to look deeper at what might be happening inside the object itself, where shifts in spin and internal mass distribution could be feeding this strange mechanical rhythm. By the time the venting sequence was confirmed, a second anomaly had become impossible to ignore. 3i Atlas wasn't spinning the same way it did before perihelion. Early measurements taken in August suggested a relatively stable rotation period of just under 9 hours, but the post-perihelion data now showed clear changes in both speed and axis alignment. The object's rotation was slowing down, gradually but measurably, and its orientation relative to the Sun had shifted by several degrees. That kind of alteration doesn't happen without a cause. For a natural body, spin rate changes are usually tied to uneven mass loss. As gases escape, they create torque that either speeds up or slows down rotation. Yet in this case, the rate of deceleration was far too steady. There were no spikes or irregularities, only a smooth, continuous drift toward a slower spin. That meant the internal forces acting on it were balanced, not chaotic. Infrared readings from the James Webb Space Telescope provided the first hints of what might be happening beneath the surface. As the object rotated, certain thermal hotspots appeared and disappeared with surprising precision. The same coordinates lit up every few rotations, cooling more slowly than the rest of the crust. This suggested pockets of material deep inside were repeatedly releasing heat at timed intervals, perhaps from trapped volatiles venting through fissures, or from mechanical stress within the core as it adjusted to the temperature swings of perihelion. If these internal pressures were oscillating, they could act like dampers, gradually redistributing angular momentum. In other words, 3i Atlas might be regulating its own spin by shifting mass inside its structure. Something a natural body could do if it were fractured into compartments that move independently. The challenge is that no one has ever observed such fine-tuned, rotational damping in an interstellar object before. The European Southern Observatory attempted to map the surface features by analysing the variations in reflected light. The brightness pattern didn't fit a simple tumbling model. Instead, it looked as if the object was precessing, wobbling around a new rotational axis that slowly migrated over time. The most plausible cause was a change in its internal mass distribution, either due to subsurface collapse or because the object was shedding material asymmetrically. Both possibilities would alter torque in predictable ways, but then another detail complicated the story. The deceleration wasn't uniform across all observation windows. There were moments when the spin rate seemed to stabilize for several hours before resuming its decline. Some scientists theorized that this might reflect a feedback mechanism, pressure building in one region until it vented enough gas to counteract the slowdown, temporarily rebalancing the motion. That kind of cyclical compensation hinted at a self-stabilizing process, whether natural or not. The Hubble Space Telescope's optical data further confirmed that the object's shape may no longer be the same. The amplitude of its light curve, how much its brightness changes per rotation, had decreased slightly. That implies either the surface has become smoother, reducing shadow contrast, or that the viewing angle has shifted due to precession. If the latter is true, then the cause axis may have migrated significantly since perihelion, pointing toward a slow but continuous reorientation of the entire body. The implications are serious. A rotating interstellar object with changing torque suggests that its internal composition is heterogeneous, regions of different density, each responding differently to heat and pressure. When those zones expand or contract, they can shift the spin rate and orientation over time. If such processes are coordinated or cyclical, they can also produce thrust effects, feeding directly into the acceleration seen earlier. In simple terms, the object's own instability could be what's propelling it. The more it flexes, the more it moves. What puzzled dynamicists was how stable the overall motion remained despite these internal shifts. Even as 3I Atlas wobbled, its trajectory continued smoothly outward. The vector didn't zigzag or oscillate as it should if random outgassing were the cause. Instead, it held steady, like a guided motion compensating for its own imperfections. At this stage, the team at the European Space Operations Centre ran simulations incorporating rotational feedback. They treated the object as a multi-layered body with delayed thermal response. Heat absorbed on one side, venting gas hours later on the opposite side as it rotated. The result was striking. The modelled body exhibited both a gradual spin down and a net directional acceleration matching the real observations. Still, this left one unanswered question. What caused the process to begin right after perihelion? If it were purely mechanical, it would have started as soon as the object began heating up. Instead, it triggered only once it emerged from behind the Sun, as though something inside reached a critical threshold and activated afterward. Some researchers speculated that perihelion had effectively reset the object's internal balance, melting and refreezing layers in a way that created new channels of pressure. Others suggested that magnetic alignment might play a role, that the intense solar field near the Sun temporarily reoriented metallic grains within the core, subtly altering how the object spins once free of the field's influence. Either way, the rotational data carried one unmistakable message. 3 Atlas was no longer the same structure it was before. It had changed in shape, rhythm, and stability, yet somehow that change had made its motion more consistent, not less. It was as though the object had adapted to its own instability, finding equilibrium through movement. And as the spin continued to slow, astronomers noticed a quieter, more puzzling effect. The radar signals returning from the object began to weaken until, eventually, they disappeared altogether. The first radar silence reports came late on the night of November 3rd. For several days, planetary radar teams had been transmitting brief pulses toward 3I Atlas using the Deep Space Network and Goldstone facilities, expecting faint reflections to help refine its shape and rotation. Until that point, every transmission had produced at least a trace echo, weak, scattered, but measurable. Then suddenly nothing came back. The operators assumed equipment failure at first. The radar arrays had just finished tracking a near-Earth asteroid, and recalibration sometimes takes hours. But repeated attempts at different frequencies yielded the same void. The signal vanished entirely, as if the object's surface had absorbed or redirected the energy elsewhere. This silence carried significance beyond technical inconvenience. Radar reflections depend on surface texture and composition. Smooth metallic surfaces produce strong echoes, while fluffy or dusty ones scatter energy away. If 3I Atlas had abruptly stopped reflecting, It implied that its outer layer had changed in a fundamental way, either coated by a new material or oriented differently relative to Earth. NASA's radar team checked for timing errors, frequency drift, and atmospheric interference, all normal. The same results were confirmed by the European Space Operations Centre and Japan's Yasuda Deep Space Complex. Across continents and wavelengths, the silence was absolute. The first explanation was dust. After perihelion, debris might have enveloped the object, forming a thick coma that scattered radar beams before they reached the surface. But optical observations contradicted this. The coma had actually thinned, not thickened. The object was cleaner and dimmer, its tail nearly gone. Whatever was blocking radar wasn't visible. One theory proposed that the rotation shift observed earlier had changed the radar cross-section. If 3i Atlas had rolled so that a highly porous region now faced Earth, radio waves could be absorbed rather than reflected. That scenario fit partially, but not completely. For the radar echo to vanish completely, the absorbing layer would need to be unusually efficient, almost like a foam of conductive particles or a blanket of carbon soot. The Hubble Space Telescope captured faint polarization changes in the reflected sunlight around the same time, hinting at a surface rich in fine metallic grains suspended in a darker matrix. It was the kind of structure that could swallow radar pulses while still reflecting optical light. Some scientists likened it to an ablative skin, material created when volatile compounds evaporate, leaving behind a residue that absorbs radiation. If perihelion stripped the outer crust, it might have reformed into this strange coating afterward. But another explanation soon began circulating quietly among research circles. The silence could also be geometric. If the object's new orientation placed its long axis edge onto Earth, most radar pulses would miss entirely, glancing off into space. Combined with its changing spin, even a small precession could keep its reflective face permanently hidden from our line of sight. To test that, radar astronomers ran simulations varying the spin axis angle, and indeed, only narrow bands of orientations could reproduce the observed blackout. Still, the timing was uncanny. The radar reflection stopped precisely as the object's optical brightness stabilized, as if the two phenomena were linked. One researcher suggested that 3i Atlas had entered what he called a low albedo phase. The dust around it recondensed into a thin, uniform coating that made it radar dark but visually steady. In other words, the object wasn't fading because it was leaving. It was cloaking itself in material that dampened both reflection and heat loss. There were other, stranger proposals. Some wondered if the material being expelled from the jets had ionized, forming a plasma sheath capable of scattering radar waves. Such behavior is known around comets interacting with solar wind, but those sheaths are transient. The one around 3i Atlas, if it existed, was persistent and symmetrical, more like a field than a tail. At the same time, magnetometers aboard the Parker Solar Probe detected subtle anomalies in the surrounding solar plasma. The readings were weak, barely above background noise, yet their timing aligned with the radar blackout period. It could be coincidence, but the alignment was hard to ignore. The disappearance of radar echoes raised deeper philosophical questions within the scientific community. If every signal sent toward it simply vanished, what did that mean about our ability to study it? For the first time, 3i Atlas was effectively invisible to active observation. Scientists could still see it with optical telescopes, but they could no longer probe its structure directly. It had crossed a threshold from being a measurable body to something opaque to our instruments. As days passed, no radar facility succeeded in regaining contact. The silence became its own kind of signal, a sign that something had fundamentally shifted, either in composition or in behavior. Some speculated that the object had vented enough gas to envelop itself in a non-reflective cloud. Others suspected the outer layer had crystallized into a dielectric surface that refracted signals away. Whatever the reason, one fact stood out. The radar loss coincided exactly with a change in how 3i Atlas reflected light. Its brightness curve flattened, becoming smoother, less variable. The object that once shimmered with irregular rotation now appeared calm, unified, and steady, too steady. And that eerie calmness extended beyond radar. As astronomers examined its visual data more closely, they realized that the brightness levels no longer matched the predicted light curve models at all. In the days following the radar blackout, attention shifted entirely to optical tracking. With radar blind, light was the only reliable means of observation, yet even that, it seemed, was beginning to defy expectations. When 3i Atlas first re-emerged from behind the Sun, it was relatively bright for its size and distance, a faint bluish object that fit standard magnitude predictions. But after November 3rd, the light curve began behaving strangely. Instead of fluctuating with its spin, as every rotating body does, its brightness started to level out, constant, unwavering, like a polished sphere turning in perfect synchronization with itself. At first, analysts welcomed the stability. A predictable light curve meant easier tracking, but when the data were compared with existing models, the numbers didn't add up. The object was reflecting less light than it should have, and its spectral color was slowly shifting. The blue tint that once characterized it was fading into a neutral gray. The change was subtle, a few percentage points in reflectance, but unmistakable across multiple observatories. The first suspicion was simple photometric error. Atmospheric conditions, calibration drift, or sensor fatigue can all distort color readings, yet the same trend appeared everywhere: Hawaii, Chile, Australia, the Canary Islands. Even space-based instruments like Hubble and Gaia detected the same uniform dimming pattern. Something about 3i Atlas itself was changing. To test the consistency, the European Southern Observatory tracked it continuously for 6 hours one night, monitoring minute-by-minute fluctuations. What they found was eerie. The brightness barely moved. Normally, a tumbling or irregular object produces small spikes as different surfaces catch sunlight. 3i Atlas, by contrast, remained perfectly steady, as if its reflective surfaces had become homogeneous, or as if the body had aligned itself to minimize variation. That possibility raised eyebrows. For the brightness to remain so flat, the rotation axis would have to be oriented precisely toward Earth. But orbital reconstructions made that alignment extremely unlikely. The odds of such a configuration occurring by chance were astronomically low. Then came another surprise. Polarimetric measurements, which reveal how light scatters off a surface, indicated an unusual degree of uniformity. Instead of the mixed polarization typical of dust and ice, 3i Atlas was reflecting light with a nearly constant angle, a property found only in smooth or metallic materials. Yet the spectral slope still pointed to a carbon-based surface. That paradox baffled researchers. How could something dark and non-metallic behave optically like polished metal? The working theory became one of restructuring. Perhaps the intense heating during perihelion had melted or fused the outer crust, forming a smooth glass-like layer that now reflected light evenly in all directions. But that didn't explain the ongoing dimming trend. Over each night of observation, the object's apparent brightness continued to fall slightly, even though its distance from Earth hadn't changed enough to account for the difference. Some scientists proposed a dust sheath, an expanding cloud of micron-sized grains around the object. This halo would scatter sunlight diffusely, making it appear dimmer and reducing light curve variation. The problem was that telescopes didn't detect the expected forward scattering signature that accompanies such dust. Others suggested that sublimated gases were condensing into a transparent shell, a kind of frozen fog acting as a reflective buffer. Still, no direct evidence supported that either. The oddest clue came from spectroscopy. A narrow absorption line appeared in the visible spectrum right where none should exist. It was faint but consistent, shifting slightly as the object moved away from the Sun. Its origin remains uncertain. It didn't match water, carbon monoxide, or any other known cometary compound. Some speculated it could be molecular nickel, consistent with earlier detections in its coma, but the line's sharpness suggested something more structured, perhaps a thin crystalline lattice forming in the cooling surface. Whatever was happening, the optical behavior now told a simple story. 3i Atlas was stabilizing, becoming smoother, darker, and optically quieter. The same object that once tumbled unpredictably across the night sky now glided like a perfectly balanced stone. It gave off less light, revealed no rotation, and reflected with mechanical consistency. That silence in light carried an unease similar to the radar void. Observers couldn't shake the feeling that the object wasn't fading, it was hiding. Every natural explanation required layers of coincidence, while the simplest visual fact remained. It had become almost featureless, as if its surface had restructured into something designed to reflect as little information as possible. By now, the brightness variation had fallen below the sensitivity threshold of most small observatories. Only the largest telescopes could still detect measurable differences, and even those differences seemed to diminish night by night. And then, as the optical flux stabilized completely, a new type of anomaly began to appear in the data, one that didn't concern light or motion, but temperature. The object, according to infrared readings, was still warm. Not hot, not glowing, but measurably warmer than its surroundings, and cooling far slower than any passive rock should. This unexpected heat retention would lead analysts into one of the most perplexing discoveries yet, an invisible signature that hinted at something happening beneath the surface. When the light from 3i Atlas began to fade, most expected its thermal signature to do the same. It was moving away from the sun, cooling naturally, and should have lost heat quickly once it passed its perihelion window. But infrared data told a different story. Even as its brightness dropped, the object remained unexpectedly warm. Not enough to radiate visibly, but enough to register as a persistent glow in the mid-infrared range, a faint, steady pulse that refused to diminish with distance. The first confirmation came from the James Webb Space Telescope. Comparing readings from before and after perihelion, scientists found that the temperature curve had flattened rather than declined. The object was cooling, but at a rate almost half as slow as expected for a body of its size and composition. In simple terms, 3i Atlas was holding onto heat far longer than physics allowed. That discovery sent teams scrambling to check for instrumental error. Calibration was verified, solar interference ruled out. Even background thermal noise from dust was accounted for. The signature persisted, localized entirely on the object. The temperature was low, barely above that of nearby space, but its stability was the mystery. It was neither fading nor fluctuating, just hovering at the same warmth, like a machine idling in standby. The prevailing hypothesis was that the object's surface had become insulated. During perihelion, volatile materials might have evaporated, leaving behind a crust rich in carbon and silicates that trapped residual heat beneath it. If that layer had compacted into something like glass or fused stone, the trapped heat could take much longer to escape. But there was a problem with that explanation. The infrared maps showed slight thermal gradients that shifted over time, as if heat were being redistributed internally rather than merely dissipating outward. The European Southern Observatory's Vizier instrument produced detailed temperature maps showing 3 recurring hotspots rotating in near-perfect intervals. Each region warmed, cooled, and then warmed again in a sequence lasting several hours. The pattern resembled cycling, almost like components taking turns releasing energy. It wasn't random thermal relaxation, it looked like a process repeating. When these patterns were overlaid with earlier optical and radar data, the alignment was unsettling. The hotspots corresponded exactly to the coordinates of the outgassing vents detected weeks earlier. In other words, the same regions that once released gas were now emitting heat without visible activity. It was as if those vents had closed but were still alive beneath the surface, continuing some form of reaction unseen from outside. Astrophysicists proposed an exotic but natural explanation: exothermic crystallization. Certain ices, when warmed near their sublimation point, can reorganize their molecular structure, releasing small bursts of energy as they solidify again. If 3i Atlas contained those materials deep inside, the repeated heating and cooling cycles could account for the steady infrared pulses. But the scale was off. The energy required to sustain those temperatures for days exceeded what crystallization could supply. Another theory focused on internal gas circulation. If the object's subsurface layers contained sealed voids, residual heat could cause trapped gases to migrate between them, transferring energy slowly through convection. This would explain the smoothness of the temperature curve, but it couldn't explain why the process appeared synchronized across separate regions. That implied coordination, whether mechanical or coincidental, on a scale unseen in ordinary cometry physics. Meanwhile, telescopes tracking the thermal emissions noticed something else. The faint heat halo surrounding 3i Atlas extended farther than before. Instead of a single point source, the infrared readings showed a diffuse region trailing behind it, a soft plume stretching along its trajectory. Analysts began calling it the thermal wake. It wasn't a tail of dust or gas, but a pocket of space marginally warmer than its surroundings, as though the object were leaving behind residual energy as it moved. The simplest explanation was delayed radiation, heat escaping slowly from released dust particles. Yet the gradient of the wake didn't match the motion of solar wind. It drifted slightly off-axis, aligning instead with the object's acceleration vector. That subtle detail made researchers pause. If the wake wasn't following solar wind direction, it might not be passive at all. The wake's shape remained stable for several nights, maintaining a faint curvature that traced the same path as the recent orbital drift. The coincidence was too precise to ignore. One researcher described it quietly in an internal memo. The object seems to be dragging a temperature field with it. It was meant metaphorically, but the phrase spread through observatory channels because it captured the oddness perfectly. 3i Atlas was moving like a body generating its own pocket of warmth through cold space. Some wondered if this was a remnant of solar energy stored deep inside, now leaking out as the object continued outward. Others began to whisper about less conventional possibilities: energy released through chemical decay, piezoelectric effects from internal stress, or even reactions between charged dust and magnetic fields. Each theory touched reality at the edges. None explained everything. The mystery deepened when data showed that the wake was not fading. Night after night, it reappeared in nearly the same position relative to the object, maintaining its shape even as the body travelled millions of kilometres. It was as though the warmth was tethered, following but not dispersing. If it were a fragment, it should have drifted away. If it were radiation, it should have diffused. Yet it held there, moving as one with the object, bound by something that telescopes could not detect. By the end of the first week of November, the phenomenon had earned official recognition within agency briefings. It was no longer a curiosity. It was categorized as anomalous thermal persistence. The cause remained unknown, and now, with heat emanating in silence and no visible material to explain it, the idea of fragmentation began to return. Perhaps the wake wasn't a field or residue at all, but the signature of something splitting. Multiple pieces moving in near-perfect formation, each contributing faint warmth of its own. When the thermal wake first appeared, scientists assumed it was a plume, the lingering warmth of dust or gas escaping from 3i Atlas. But as observations accumulated, that explanation started to crumble. The wake didn't spread or dissipate as dust should. It held its shape and brightness relative to the object, almost as though it were tethered to it. That's when analysts noticed something subtle in the data. Faint optical irregularities along the wake's axis, points of light that flickered in near synchrony with the main body. At first, these were dismissed as background stars or digital noise, but repeated imaging over several nights proved otherwise. The points moved. They followed the same general trajectory as 3i Atlas, maintaining fixed distances from it, like faint companions orbiting a shared centre of mass. Once the pattern became undeniable, the discussion shifted from thermal anomaly to fragmentation event. Had the object broken apart during or after perihelion? If so, how could the fragments remain so perfectly aligned? Fragmentation is common in comets. As solar heat builds, internal gases expand and tear the nucleus apart, sending debris drifting in a loose trail. Yet 3i Atlas's fragments, if they were fragments, showed none of that chaos. There was no fan-shaped debris cloud, no broadening tail. The new points were evenly spaced and faintly luminous, each echoing the main body's motion, as though connected by invisible threads. The European Space Agency's Near-Earth Tracking Division conducted a high-resolution analysis using stacked imagery to increase contrast. Their findings were startling. The trailing region wasn't a continuous haze. It contained at least 4 distinct thermal nodes, each separated by almost equal distances. More remarkably, each node emitted a faint infrared signature consistent with retained heat, identical to the main body's temperature profile. In natural fragmentation, smaller pieces cool faster. These, however, remained warm. That meant either they were larger than they appeared, or heat was being transferred between them. To test the idea, the James Webb team ran photometric comparisons of all visible nodes. The brightness ratios stayed consistent over 3 nights, even as viewing geometry changed. No tumbling, no random fading, just steady, synchronized light. That level of stability made no sense for free-floating debris. A leading hypothesis emerged. The object hadn't shattered, it had separated. Instead of a destructive breakup, 3i Atlas might have undergone a controlled disassembly, dividing into multiple self-stabilizing segments that now travelled in precise formation. The idea sounded absurd, but the data pointed in that direction. The spacing between the fragments was too regular for a chaotic event. The velocities matched within observational precision. Even the thermal emissions pulsed in the same rhythm. If they were independent bodies, some form of coordination was maintaining their arrangement. Scientists searched for simpler explanations. Could optical interference be creating the illusion of multiple points? Simulations said no. Could gravitational forces from internal mass redistribution eject chunks along an axis? Possibly, but that would scatter them, not align them. Could the wake represent light reflecting off jets? Not unless those jets remained constant for days, which they didn't. By November 5th, observatories confirmed the structure definitively. 3i Atlas was no longer a single object. It was a small convoy of bodies, each following the same hyperbolic trajectory, spaced evenly in a pattern unlike anything previously observed in the interstellar objects. What made this particularly unsettling was the geometry. The spacing between fragments followed an almost harmonic ratio, each one twice the distance from the previous. It resembled a distribution engineered for stability, the kind of arrangement used in satellite formations to avoid interference. For natural debris, that kind of spacing would be a coincidence bordering on impossible. Of course, no one publicly used the word engineered. The official statements remained cautious. Fragmented configuration with coordinated motion. But within the community, discussions turned private and uneasy. Some suggested that perihelion heat had triggered internal fractures along pre-existing lines, splitting the object cleanly into similar sections. Others pointed out that if that were the case, those pieces should be drifting apart faster. They weren't. Spectroscopic comparisons confirmed that all fragments shared identical composition signatures, carbon, nickel, and silicate traces, yet the spectral slopes hinted at slight differences in surface texture. One fragment appeared smoother, another darker, as if each piece carried a different layer of the original body's structure. That detail fueled speculation that the fragments weren't random chunks, but distinct components of a once unified whole, parts that were meant to come apart. If so, then perihelion didn't destroy 3i Atlas, it activated it. Still, mainstream researchers remained grounded. They argued that interstellar ice structures could fracture predictably along crystalline planes, creating evenly sized segments. Under solar heating, such fractures might release gas in symmetrical bursts, giving the illusion of coordinated motion. The fact that no dust trail was visible remained a challenge, but it was better than admitting the alternative. Privately, however, one analyst from the ESA's optical division summed up the unease in a simple line. Natural or not, it's moving with purpose. As the fragments continued outward, telescopes tracked their positions meticulously. The spacing between them did not change. The convoy glided in silence, each body reflecting faintly in the same rhythm as the next. No one could tell whether they were communicating, connected, or simply obeying the same physical impulse. But whatever force had caused the separation was still active, and as this silent procession stretched farther from the sun, analysts noticed something new. The fragments weren't just maintaining distance, they were beginning to accelerate again, together, as if guided by the same invisible hand. When the fragments of 3i Atlas began accelerating in unison, the mood across observatories changed from curiosity to quiet alarm. A natural breakup should have produced gradual divergence, fragments spreading out as the parent body's momentum dispersed. Instead, what researchers saw was collective motion. Every piece, from the largest central fragment to the faint thermal nodes trailing behind, was gaining speed at the same rate, as though responding to a single command. The European Space Operations Centre released an internal note describing the phenomenon as a non-gravitational acceleration event affecting multi-body formation. The language was deliberately cautious, but behind that restraint was disbelief. No one could explain how several independent fragments could accelerate simultaneously and maintain perfect spacing across tens of thousands of kilometers. At first, scientists suspected radiation pressure variations, the sun pushing more strongly on certain surfaces causing apparent synchronization. But calculations quickly ruled that out. The effect was far too coordinated. The fragments moved like points on a rigid frame, each mirroring the other's motion precisely. Even their subtle oscillations matched as if they were tied together by an invisible field. Then came a discovery that deepened the puzzle. During one of the synchronized accelerations, magnetometers aboard the Parker Solar Probe and ESA's Solar Orbiter detected a faint rhythmic fluctuation in the surrounding magnetic field. The signal repeated at intervals consistent with the timing of 3I Atlas's acceleration surges. It was weak, almost buried in noise, but unmistakably periodic. Analysts called it a coincident geomagnetic pulse. No one could tell whether the object caused it or was merely reacting to it, but the timing was too exact to ignore. At NASA's Goddard Space Flight Center, plasma physicists ran models to see if ionized gases venting from the fragments could create a shared electromagnetic sheath, a kind of collective cocoon. In theory, charged particles emitted from one body could interact with those from another, forming a tenuous plasma bridge that transfers energy between them. If that bridge were stable, it could explain the synchronized motion, but to maintain such coherence over the observed distances would require constant regulation, something no known natural process could achieve. As data poured in, astronomers noticed another detail. The acceleration wasn't linear, it came in waves. Every few hours, the speed of the formation would increase slightly, then plateau, then increase again. The rhythm was so steady that researchers began plotting it as a timeline, and what emerged resembled a repeating signal rather than a random pattern. This is where debate turned philosophical. Some saw in that rhythm a purely mechanical process, cycles of gas pressure building and venting across multiple fragments. Others quietly admitted that it looked eerily deliberate, like synchronization between coordinated modules. One astronomer from the University of Cambridge wrote in a private correspondence, "We are seeing behavior, not reaction." These pieces are acting as one system. No one dared say it publicly, but the comparisons to artificial behavior began circulating among late-night discussions and encrypted channels. The word craft appeared in a few internal messages, quickly redacted before reports went to press. The official line remained, 3I Atlas displays anomalous, collective non-gravitational acceleration, cause under investigation. Even those who rejected any non-natural interpretation agreed on one thing: the force driving 3I Atlas was not random. Its direction remained consistent, always away from the Sun, slightly tilted along its ecliptic trajectory, a path that grew more linear with each day. By November 6th, simulations showed that if the current acceleration continued, the formation would exceed escape velocity from the solar system within a matter of weeks, leaving our observational range before the end of the year. But the question remained, what was providing the energy? Outgassing had stopped, radiation pressure was too weak, and gravitational influence from nearby planets couldn't account for the pattern. A few theorists proposed magnetic induction. If the fragments contained conductive material, movement through solar plasma could generate currents, creating thrust-like effects. Yet such a mechanism would require precise alignment and phase matching between all pieces, exactly what the data showed. There was also the issue of silence. Throughout all these changes, fragmentation, synchronization, acceleration, not a single trace of radio emission had been detected. No narrowband signals, no pulses, nothing resembling communication. Whatever was coordinating the motion was doing so silently, through means invisible to current instruments. Some researchers suggested that the hidden force might not be an external one at all, but an emergent property of the formation, the combined effect of thermal gradients, magnetic interactions, and internal stress acting together in a self-regulating loop. If true, 3I Atlas could be exhibiting a new kind of natural physics, one in which structural feedback allows a body to maintain stability through continuous adjustment. It would be the first known example of a self-balancing interstellar object. But the term self-balancing carried uncomfortable implications. It implied control, even if unintentional. A system capable of regulating its own motion blurs the line between mechanical and biological behavior. Was 3I Atlas a relic of some unknown natural process, or a remnant of technology built long before our civilization ever looked skyward? In the meantime, telescopes observed something even stranger. As the formation continued outward, its infrared glow began to fade not gradually but in pulses, synchronized with each acceleration wave. It was as though heat was being exchanged between fragments, stored, transferred, and released in rhythm. The process looked deliberate, efficient, and coordinated. By now, the observational data were undeniable. 3I Atlas was no longer a drifting interstellar rock. It was a system operating with cohesion and rhythm across multiple bodies, governed by a force that no existing model could explain. As analysts prepared to update its orbital parameters again, they realized something else. The predictive models were now completely useless. No simulation could project its next position with accuracy beyond a few hours. The object had entered a regime of motion unbound by classical mechanics, or at least not by any mechanics we currently understood. And as the hidden force continued to propel it farther into the dark, a new failure began to unfold. The predictive software itself, the same algorithms used to model asteroids and comets for decades, started to crash whenever new data were entered. The orbit of 3I Atlas had become mathematically unstable. When the orbit models for 3I Atlas started collapsing, the first assumption was human error. For decades, the same predictive software had accurately tracked millions of celestial objects, from tumbling asteroids to faint Kuiper belt debris. But now, as soon as analysts entered the latest tracking data, the programs failed to converge. The numbers refused to settle into a coherent path. Instead, they spiraled outward in endless feedback loops, as if the algorithms were chasing something that kept moving out of reach. Normally, orbital instability arises from incomplete data, missing measurements, bad timestamps, faulty coordinates. But this wasn't a data gap. The input from multiple observatories, each independently verified, matched perfectly. The equations simply couldn't reconcile what they were seeing. 3I Atlas wasn't following any trajectory that gravity alone could describe. The first sign of serious trouble came when NASA's JPL Horizons system generated a projection that diverged after only 12 hours. Instead of plotting a smooth curve, it produced an expanding cone of uncertainty that doubled with every iteration. Within a day, the projected path filled half the inner solar map. By the next morning, the simulation stopped running altogether. It couldn't process the next update. The object's position contradicted its own predicted future. At ESA's Flight Dynamics Division, engineers attempted to recalibrate the models by introducing new variables: radiation pressure, outgassing, fragmentation, plasma drag. None of them improved the fit. The residuals between predicted and observed positions grew larger with every pass. The system treated 3I Atlas as if it were constantly resetting its own velocity vector, like a spacecraft performing micro-adjustments that no one could see. Within days, model divergence became the standard entry in agency logs. The same message repeated across organizations: trajectory cannot be predicted. Some analysts refused to accept that conclusion and began experimenting with nonlinear algorithms, hoping chaos theory could account for the erratic data. But even those models broke down. The object's motion was too clean to be random and too inconsistent to be deterministic. When researchers visualized the residuals, the small differences between expected and actual positions, an unsettling pattern emerged. The points didn't scatter randomly across the plot. They formed a spiral. The shape repeated in every dataset, no matter the telescope or coordinate system used. That spiral suggested an internal logic, as though each correction the object made was part of a continuous path invisible to our equations. The discovery sent quiet ripples through the community. One physicist called it the first orbit that refuses to be solved. Another described it more poetically: we're watching an object that's choosing its own future. The phrase was never meant literally, yet it captured the feeling perfectly. 3I Atlas wasn't chaotic, it was self-consistent on terms we didn't understand. In desperation, teams began using machine learning systems trained on past orbital anomalies, feeding them every data point available. These neural networks didn't crash, but the results were no less perplexing. Instead of a trajectory, the models generated a moving boundary, a volume of probability that shifted smoothly through space, like a phantom corridor. The object's actual position always fell inside that corridor, as though following a rule not written in classical mechanics. At the European Space Operations Centre, an analyst noticed something even more peculiar. When the simulations were allowed to run past their divergence points, the virtual trajectories began looping back toward the Sun, not physically, but mathematically, as if the object's influence persisted in equations long after it left the inner system. In his report, he described it as a resonant shadow, a pattern of numerical echoes that repeated with every new attempt to stabilize the orbit. These shadows appeared even when the software was reset and reinitialized, leading some to speculate that the problem might not lie in the data, but in the fundamental assumptions of the models themselves. They were built on the idea that all motion is deterministic, governed by gravity and external forces. But what if 3i Atlas was operating under feedback from within, a closed system adjusting to its own state in real time? The algorithms weren't designed to model decision-making, only reaction. In practical terms, this meant something simple but alarming. Humanity could no longer predict where the object would be next. Every night's observation became an act of rediscovery. Telescopes could only point to where 3i Atlas was last seen, and hope it remained nearby. More often than not, it had already moved. The breakdown of simulations wasn't just a technical failure, it was a conceptual one. For the first time in modern astronomy, an interstellar object was behaving according to rules outside the predictive reach of physics. It wasn't defying gravity, it was supplementing it with something else, something dynamic and adaptive. By November 7th, most agencies stopped releasing public trajectory updates altogether. The official reason was data integrity review. Privately, the reality was simpler. No one wanted to publish guesses that would be disproven within hours. In private briefings, senior scientists spoke of the situation in measured tones, but the implications were clear. Humanity had lost track of an object that wasn't lost, only unpredictable. The last reliable position came from Chile's Cerro Paranal Observatory, which captured the formation still intact, its fragments faintly glowing in the infrared. After that, no telescope could confirm its coordinates. When plotted on the solar map, its predicted path dissolved into statistical fog, a moving void where calculations once were. It wasn't vanishing, it was escaping the very framework by which we understand motion. In the silence that followed, as simulations failed and tracking screens went blank, a quiet realization spread through the scientific community that this object, whatever it truly was, had reached the limit of our equations. It was no longer something to be modelled, only something to be watched. And yet, even as the orbit collapsed in math, the data from deep space instruments revealed something else, faint but impossible to ignore. A pulse repeating in the background, regular and distant, moving outward along the same vector the object once followed. Data streams of several deep space instruments. It repeated every few minutes with near perfect regularity, then faded below the threshold before returning again. It carried no message, no modulation, nothing that looked engineered. Yet its timing and direction aligned precisely with the vanished object's last known trajectory. That discovery split the scientific community. One side argued for a mundane explanation: instrumental interference, sensor feedback, or the echo of solar plasma interacting with residual dust. The other side, a smaller but growing minority, insisted the pattern was too coherent to be noise. They called it a sustained directed signal of unknown natural origin. That phrasing became the cautious compromise used in the internal documents. The debate that followed was unlike anything since the Oumuamua controversy years earlier. But this time the evidence was sharper. There were no ambiguous shapes, no pixelated images, just numbers. And those numbers implied rhythm, repetition, and intent. At NASA's Goddard Space Flight Center, analysts compared the pulse interval to the timing of the acceleration waves recorded before 3i Atlas vanished. The intervals matched exactly. It was as if the same force that once drove the object outward was now resonating through space, echoing along the path it left behind. For some, that connection meant the object was still active. For others, it simply meant that we were listening to the lingering vibration of an event long over. The question soon turned from what is it to how much do we tell? Officially, agencies maintained a strict position. 3i Atlas remained a natural interstellar object, exhibiting unexplained behaviour during post-perihelion evolution. Unofficially, the conversation had shifted. Closed scientific meetings began using the term technogenic hypothesis, a phrase borrowed from astrobiology, meaning possibly created or altered by technology. The word artificial was avoided, but its implication filled the silence between every line of the reports. Those who supported the technogenic idea didn't claim that 3i Atlas was a spacecraft. Most believed it could be debris, or a fragment of a larger structure that once moved through interstellar space under its own power. The synchronized fragments, the consistent acceleration, the impossible orbital adjustments, all could point to remnants of a mechanism, one that had partially survived and partially decayed over time. Their opponents countered that calling it artificial solved nothing. It simply moved the mystery from physics to speculation. They argued that invoking intelligence without direct evidence was unscientific, that the data could still fit within exotic but natural processes. Perhaps 3i Atlas was made of layered materials that reacted to solar exposure in ways not yet documented. Maybe electromagnetic forces in the heliosphere triggered resonance between fragments. Nature, after all, often behaves in ways that mimic design, but the facts refuse to cooperate with skepticism. The synchronized acceleration had been recorded independently by multiple observatories. The radar silence, the perfect spacing, the constant heat retention. None of these behaviors matched known natural models. Each one could be explained individually, perhaps, but together they formed a pattern that resembled function. Then came a leak. A scientist from an unnamed European institution anonymously released a short report summarizing internal discussions under the title Potential Controlled Dynamics in Interstellar Object 3 Atlas. The document was careful, even understated, but its phrasing was unmistakable. Observed behavior suggests regulation of momentum inconsistent with spontaneous outgassing or radiation pressure. A model involving residual control mechanisms, either biological or mechanical, cannot yet be excluded. The report spread across the internet within hours, sparking headlines that blended fact with speculation. Words like craft, probe, and non-human technology flooded social media. For the scientific community, it was a disaster. Years of careful caution undone by a single paragraph. Agencies scrambled to issue denials, calling the leak premature and misleading. But by then, the public narrative had already shifted. Inside observatories, the atmosphere grew tense. Researchers who had quietly leaned toward the artificial hypothesis began facing scrutiny. Funding bodies worried about public perception. Meetings became divided between those who wanted to confront the anomaly head-on and those who feared the consequences of drawing conclusions that sounded like science fiction. Amid the controversy, one simple observation kept the debate grounded. The pulse hadn't stopped. Night after night it continued, growing fainter as it moved outward but never breaking rhythm. If it was interference, no one could find the source. If it was a reflection, there was nothing left to reflect. A senior astrophysicist at the European Southern Observatory put it best during a closed debrief. We may not be witnessing technology, we may be witnessing memory. Whatever 3i Atlas was, it left an imprint that space itself is still carrying. That idea, that space could hold a residue of order long after its origin vanished, struck a nerve. It bridged both camps. Those who believed in natural explanations saw it as proof of a rare, self-sustaining physical process. Those who suspected design saw it as evidence of intent, something that wanted to be remembered. By mid-November, the debate was no longer about what 3i Atlas was, but what it meant. If intelligence could leave behind relics indistinguishable from nature, or if nature itself could produce behavior indistinguishable from design, then either answer carried the same implication: our definitions were incomplete. And as the arguments continued, another silence began to spread through the data channels. The pulse, steady for nearly a week, suddenly stopped, not fading, not weakening, just ceasing altogether at a single, precise moment. It didn't decay like a dying signal. It ended like an action completed. What followed was not discovery, but absence, a perfect mathematical quiet that felt deliberate in itself. And that silence became the final data point in the record. The end of the pulse marked the beginning of something even stranger. Within minutes of its disappearance, multiple deep space listening arrays across 3 continents reported simultaneous system errors. Receivers in Australia, Spain, and California, all tuned to unrelated projects, recorded an identical surge of static at the exact timestamp that the 3i Atlas signal went silent. It lasted less than 2 seconds, a narrowband distortion that briefly overpowered baseline noise, then vanished completely, leaving the systems fully operational yet empty of data from that moment onward. Technicians initially blamed cross-interference or a minor solar event, but no flare had occurred and the arrays weren't networked. The static spike had no known source. It arrived from a vector matching the last trajectory of 3i Atlas, as though the silence itself had arrived in the form of a wave. From that point on, the universe grew quieter, not metaphorically, but literally. Instruments that routinely recorded the faint hum of cosmic background radiation began showing irregular gaps. The gaps weren't absences of data, they were regions of perfect flatline, measurable silence where background noise should exist. For the first time in decades of continuous observation, the detectors registered sections of the cosmos that emitted nothing. When these gaps were plotted across the sky, they formed a thin, sweeping arc following the same direction as the vanished object. The pattern became known among observatories as the Atlas Line. No agency released that name publicly, but it spread through internal emails and private research logs, written always in lowercase. Atlas Line, as if lowercase somehow made it less ominous. The first to notice the line's movement was the South African Radio Astronomy Observatory. Over several nights, the arc drifted gradually across the sky, advancing along the path 3i Atlas had taken as it left the inner system. It moved with such precision that researchers realized it wasn't a random data artifact. The silence was traveling. When word reached NASA and ESA, both agencies temporarily suspended external access to deep space telemetry archives. The official explanation was data synchronization maintenance. Privately, teams were instructed to isolate the arrays affected by the blackout and cross-verify against optical and infrared instruments. Every check came back the same. The affected region of space wasn't invisible. Stars still shone through it. But any signal passing through the area lost coherence. Radio, microwave, even certain optical wavelengths were subtly distorted, as though travelling through a thin veil that absorbed not light, but order. To the public, nothing appeared unusual. No images were released, no announcements made. But within the scientific network, unease spread like a rumour that everyone knew was true. Something about 3i Atlas's departure had changed how a portion of space behaved. Theories multiplied. Some called it a plasma remnant, a sheath of charged dust interfering with electromagnetic transmission. Others suggested that the silence zone might be the wake of the object's movement, compressing the local medium like the aftershock of a sonic boom. Yet no known interaction could dampen frequencies so precisely, or maintain coherence across millions of kilometers. The blackout behaved less like a cloud and more like a field, invisible, structured and moving deliberately outward. At the SETI Institute, engineers attempted to redirect older antennas toward unaffected sectors to ensure the problem wasn't local. The instruments worked flawlessly elsewhere. Only along the 3i Atlas vector did the silence persist. One analyst described it bluntly: "We can see through it, but we can't hear through it." For researchers, that silence became its own kind of transmission, a message made of absence. Some believed it was simply the physical echo of whatever mechanism had once driven the object's acceleration. Others whispered, half-jokingly, that perhaps the silence was intentional, the final act of an intelligence that preferred to leave quietly. By November the 10th, the blackout had expanded enough to interfere with several deep space communication relays. Probes at the edge of the solar system briefly lost telemetry before regaining signal. The disruptions followed no pattern except proximity to the Atlas Line. It was as if a moving horizon was sweeping outward, swallowing radio contact and returning it unchanged but muted. Still, every attempt to measure the phenomenon more precisely failed. Data corrupted on transmission, instruments froze mid-collection, and simulation software locked up when the coordinates of the silence zone were entered. The same numerical instability that once plagued the trajectory models now appeared in the analysis tools themselves. A week later, the last confirmed position of the line was reported far beyond the orbit of Neptune. After that, tracking data went blank. The silence passed beyond reach, too faint, too distant, too stable to measure. Then, on November 17th, something unexpected happened. All the arrays that had gone quiet suddenly came back online, perfectly synchronized, with normal background noise restored. The blackout ended as abruptly as it began. No residuals, no trace of interference, nothing in the data to suggest the silence had ever existed. To this day, no one has explained where it went, Some insist it was an electromagnetic mirage, a byproduct of software instability. Others maintain that what humanity experienced was the first measurable trace of a phenomenon that defies every known law of energy transmission. Whatever the truth, 3i Atlas was gone. Not destroyed, not hidden, simply absent, leaving behind a brief, inexplicable quiet in the noise of the universe. And as astronomers resumed normal operations, they noticed one last unsettling detail. When the background noise returned, it wasn't identical to before. The spectrum looked the same, the amplitude unchanged, but there was a narrow repeating gap in the cosmic hiss, a single frequency missing, a silence folded inside the sound. It wasn't enough to hear, but the instruments did. The universe was no longer broadcasting on the same channel. By the time the silence lifted, the world had already moved on. Publicly, 3i Atlas was just another interstellar visitor, a curiosity that came, confused us, and disappeared back into the dark. The official archives reduced the event to a handful of dry bullet points: anomalous acceleration, trajectory loss, and temporary communication interference. The story ended there, at least on paper, but inside the observatories, the scientists who had followed the object from the start knew that nothing had truly ended. The data had stopped, but the implications hadn't. When the radio arrays came back online, the first thing everyone checked was whether the Atlas line, that narrow moving silence, had left any trace. It hadn't. No measurable disturbance remained in the cosmic background. Yet the instruments themselves weren't the same. Each receiver now contained small, identical calibration offsets, tiny shifts in their internal timing, as if all of them had been synchronized by an external pulse. No one could explain how that was possible. At NASA's Jet Propulsion Laboratory, technicians compared system clocks against Earth's atomic standard and found them perfectly aligned. Too perfectly. The synchronization tolerance was finer than the systems were designed to achieve. It was as though every clock had been corrected to a common reference not available anywhere on Earth. Engineers shrugged it off as a coincidence, but a few quietly wondered if that final static surge, the one that hit every station the moment the signal ended, had done more than disrupt communications. The last confirmed data packet from the Deep Space Network contained something else, almost unnoticed at first. Embedded within the static, hidden in the noise floor, was a brief modulation. Not a message, not even a pattern, but a deviation from randomness itself, a kind of mathematical order that shouldn't have existed in background noise. The pulse was too short to decode, too faint to analyze, and yet it appeared across every dataset on every continent. It was there, then gone, like a whisper folded into silence. By the end of November, the trail of 3i Atlas had stretched beyond measurable space. The projected vector pointed toward the outer heliosphere, a region so far that no ground-based telescope could track it. The object, or the formation that once was, had crossed the boundary of observation. It was beyond radar, beyond optical range, beyond all practical reach. But something curious lingered in the telemetry logs. A persistent, minuscule gravitational residual that shouldn't exist. The solar system's overall momentum vector showed a correction of the smallest measurable fraction, as if something of mass had left it, yet not entirely. Physicists called it a rounding error. Others weren't so sure. If 3i Atlas had indeed left behind some kind of field, a wake, a distortion, or a remnant of its acceleration, then perhaps the solar system itself now carried its fingerprint. The math hinted at a faint asymmetric distortion in local gravitational mapping, invisible to all but the most sensitive instruments. It was tiny, but real enough that simulations had to be recalibrated to account for it. In every new orbital model, that correction was simply labelled Atlas Residual. Meanwhile, a few scientists kept watching the edge of the solar system, where Voyager and Pioneer signals still trickled in from interstellar space. Nothing unusual appeared in the data, except for one detail. Every deep space probe operating beyond the heliopause began showing an identical phase shift in their carrier signals, a delay too uniform to be random. When plotted against the path 3i Atlas had taken, the delay lined up perfectly with its last known vector. It wasn't communication, and it wasn't interference. It was simply a reminder, a microscopic echo showing that the object's influence had not disappeared. Something was still out there, changing the medium through which even light and radio waves moved. The international agencies eventually closed their investigations, their final reports ending with the same phrase: the object's current location is undetermined. But those who had followed every anomaly, every deviation, every silent rhythm, knew that undetermined wasn't the same as gone. It was the word you used when the rules no longer applied. And so, 3i Atlas passed into history, not as a mystery solved, but as a boundary crossed. It left behind no fragments, no transmissions, no light, only silence, precision, and the smallest shift in how we understand motion itself. Late at night, some astronomers still monitor the sector where it vanished, not expecting a signal, only the faint comfort of data returning to normal. But sometimes, in the background of an unrelated observation, a comet, a quasar, a patch of empty space, they find something they can't quite dismiss: a missing frequency, a brief pulse of noise, a reading that doesn't fit. And when that happens, they all do the same thing. They check the timestamp, compare the coordinates, and quietly look toward the same empty stretch of sky. Because deep down, everyone knows the truth that official reports won't print. 3i Atlas never stopped moving. It simply moved beyond what we can measure, a path unresolved, continuing somewhere past the edge of prediction, into a silence that still remembers its name. No new data has arrived for months. The archives are closed, the teams reassigned, and the name 3i Atlas has already faded from public memory. But among those who watched its trajectory dissolve in real time, there remains a shared understanding that the event never truly ended. When they speak of it now, it's never about what the object was, but what it changed. Every system that interacted with it, radar, infrared, magnetic, gravitational, recorded a deviation, a pause, or a silence that could not be replicated. Even after all the instruments were reset, a faint pattern of synchronization persisted in the background noise of Earth's own sensors, as if some invisible metronome had been set ticking just beyond perception. Some call it coincidence, others quietly think it was a form of calibration, a handshake between whatever 3i Atlas was and the tools built to find it. Maybe it wasn't trying to communicate at all. Maybe it was only aligning us to listen. The mystery now belongs to deep time. Long after the data fades from our networks, 3i Atlas continues on its course into interstellar space, silent, untracked, but never still. Whatever force moved it beyond prediction still moves it now, carrying it toward regions where sunlight never reaches, where even radiation has no direction. One day, perhaps centuries from now, another civilization might intercept the faint trail of its motion, not as light or signal, but as a subtle distortion in the field that defines reality itself. They will measure it, question it, and wonder who else once stood on a small planet, staring into that same void, trying to give it meaning. For now, all that remains is the quiet it left behind. A silence threaded through every spectrum, subtle yet permanent. A silence that makes every new signal feel slightly different, slightly out of tune. And maybe that's the legacy of 3i Atlas. Not discovery, not fear, not proof of anything, just awareness. A reminder that even in a universe ruled by equations, there are moments when the math stops working and something else takes over. Something that watches, waits, and then simply moves on. No transmission, no echo, no return signal, only direction. Precise, patient, and infinite.